There we go. Everybody, welcome. Thanks for showing up. Let me make an announcement before I give Adam the floor. Dr. Wade, we see up here on the screen is actually teaching a course, geometry, next semester, and I'm going to let her speak after Adam stops, give it a little plug. So stay tuned for that. For right now, I give you Adam Price, who's going to talk about hyperbolic space and manifolds.
Want to make sure that I can see myself. Or maybe not. Okay. Yeah. So, I've been told that this is a bit of an ambitious talk that I've tried to put together. So, it's entirely possible that I might not get through everything that I want to get through, but we're going to see how much we can get. I'm at least going to get into hyperbolic space. But what I want to do today is I want to introduce you guys to a few more advanced topics in math. But first, I want to confront that topic, advanced, or confront that word, advanced, because generally speaking in math, we try to build on things that came before. So if you have some sort of a new concept that hasn't yet been fully explored, you generally want to try to apply previous methods to approach it. Or if you don't do that, you're going to have to rebuild from the ground up and recover about 2,000 years worth of development. So if you're in a situation where previous tools don't necessarily apply to the correct thing that you're trying to analyze, it's going to be difficult no matter how you do it, even if the basic concept isn't too much to wrap your head around. I want to present these things in a way that you can appreciate the underlying concept, but I might gloss over some of the math, because the math is difficult. You guys try to apply. Well, difficult places. But the specific topics that I want to talk about are manifolds and hyperbolic space. The way that these things overlap is that they're both connected to Euclidean space, which was named after this guy. Euclid. Now, this guy, Euclid was one of the very first mathematicians to do things the way that we do them nowadays. In fact, I think that he might have been the very first, where he presented a collection of axioms, postulates, and then built up from there to more and more non-trivial things. He went from just a series of 5 assumptions that he makes and goes up from there. Nowadays, we do this all the time. We use Zermelo-Fraenkel axioms, we use group theory axioms, all that stuff. But Euclid started with these 5 postulates. He was trying to understand geometry. And the thing is, these assumptions, when we're working with math, it's all abstract in our heads. We can't necessarily be working with examples all the time. But you can't get a hold of anything unless you have rules in place. So you have to have assumptions. Inherently, these assumptions are limiting, but what assumptions do you have? Well, these are the 5. First, you guys know Euclidean geometry already, right? Like you guys have had a geometry course. You know all the rules of planes, circles, and all that. These 5 assumptions allow you to build up from nothing to all of Euclidean geometry. You start out, if you have any 2 points, this first assumption, if you have any 2 points, you can connect them with a line segment, straight line segment. So, right? If you have a line, that's the first one. If you have a line segment, you can extend it into a longer line segment indefinitely. And so you have a concept of a line. You can go off in either direction. And this seems obvious to us. It's just the concept of a line. But you have to keep in mind, back when Euclid was around, people might have thought because they would say, you're going to run out of blackboard eventually, right? But nowadays, we're more comfortable with the idea of going on for forever. We have an infinite line. That's the second stage. Well, maybe not. Third, if you have a point and a radius, you can define a circle. All the points that are that distance away from the point. Another thing that Euclid assumes you can just do. Third, if you have a right angle and another right angle, they're the same size. And this controls how behavior around a point works. You can fit 4 right angle corners around a single point. It's the same sort of thing with like triangles. If you have 60 degrees or pi over 3 radians, I suppose, you can fit 6. And then, so those are the first one, all fairly basic, things that you wouldn't naturally want to assume. These are things that, if these aren't true, then what is true? Like if you don't have these, what do you have? But the last one is the big one. This is one that was kind of controversial for about 2,000 years because everybody wanted to say that you didn't need it. You could prove it from the other 4. Turns out you can't, but we'll get to that later. The parallel postulate, special. It states that if you have a line, any old line, and any point not on that line, you can draw a unique line through that point that never meets the original line. So the basic things is you can draw a line that never meets this, and it's unique. That gives rise to Euclidean geometry, and this one is the big one. If you change it, things get weird, and we'll get into that later. That's what hyperbolic space is. All right. If you have a space which satisfies these 5 postulates, then you have an example of Euclidean space. This Euclidean space is the space of flat things. It's the space, it's the geometry of this room, of a window, of a road, of a city, of a floor. Here you can notice that we have a square tiling on the floor. So Euclidean geometry. The space of a blackboard. That's why I can draw. There's lots of examples of Euclidean space. You can go 2-dimensional, you can go 3-dimensional, you can even go up to 1 trillion dimensions. If you guys have been keeping track of ChatGPT, that is working inside trillion-dimensional Euclidean space. Jeez, interesting to think about that. But not everything is captured by Euclidean space. Those assumptions that Euclid had, they're all reasonable assumptions. If you put them up, then you can say a lot of things about the space that satisfies those axes. But it doesn't describe everything. It assumes that things are flat. But not everything is flat. Can you guys think of an example of something that's not flat?
Sphere.
A sphere, yeah. An easy and immediate example is the Earth. So, I'll just go straight into the next slide. It's possible to construct a series of 3 straight paths on the surface of a sphere. So I put on my Jesus shoes, put on my sober shirt so I don't freeze in the early. I just start on the equator and start walking in a straight line across the equator. I go maybe 1/4 of the way around the Earth, then I turn left, go all the way to the North Pole, then I turn 1/4 of the turn to the left, I go all the way back down to the equator, and then I turn left again, I'm pointed back the way that I originally was. That was 3 90-degree turns, but it's a triangle. It's entirely possible to, on the surface of the Earth, construct something that satisfies the description of a triangle. A shape bounded by 3 straight lines, where none of the interior angles don't sum to pi radians. In fact, on the surface of the sphere, it is necessary that the sum of the interior angles is greater than pi. And that's not something I'm going to prove, but it's a very interesting fact. How can this be? We're on the Earth, and I just said that this room follows Euclidean geometry. So what's the deal? The thing is that you notice how the curvature impacts geometry until you get up to a large size, until this curvature starts to matter. If you're just working at a local region, in a room, in a city, you can map that with Euclidean geometry and lose very little information. Like, this is a map of Amsterdam, and this is a map of Europe, which I didn't notice until I was going through my slides later, that it's actually from the 12th century. So, it's a bit of a surprise. But this map over here, it's a map of an entire continent. So it has to take into account the curvature of the Earth. The big issue is that whenever you try to take spherical geometry and map it to Euclidean geometry, you have to warp it. This is why Euclidean geometry is not really equipped to describe everything. But we're used to using Euclidean geometry, so we're trying to, like every time we try to study a new concept, we try to foist Euclidean geometry onto it. But this is something that we do with the Earth all the time. We have to map it. And so we compile these books of maps, an atlas, where each region, you take the region and you flatten it out onto Euclidean space so that you can get an understanding of it. This is where our first tangent comes up. A manifold is something that has this kind of behavior. The behavior where you can map it locally to Euclidean space. So if you have a manifold and you're just walking about on a particular region of that manifold, you can map it with a flat sheet of paper. You can draw it. You, of course, have to potentially twist or warp it, but that's what a manifold is. Formally, this is a little bit of math. We say that X, a set, is a manifold if there exists an atlas on it. And an atlas on X is a collection of sets and functions. U alpha is a set, B alpha is a function, and it's indexed by some set. So for everything in I, there's one pair. Each UA is a subset of the manifold. It's a thing contained on the manifold. So if you're talking about the Earth, it's a region. It's a patch of the Earth. And each phi alpha is a map from that region to Euclidean space, or you flatten it out. So you could, and some of the requirements is that each part of X is contained in at least one U alpha, and it has to go into Euclidean space homeomorph. Don't worry about what homeomorphically means if you don't know. But you want it to preserve some sort of structure, some shape of the space. And these are very useful for like describing mountain chains, migration patterns, structures, things that are visible on a global scale. There are a lot of manifolds out there because this is a very general kind of thing. You can talk about any kind of space, a whole bunch of subsets, and you can talk about mapping them into the Euclidean space. You can do it arbitrarily. I can't talk about all of them in a talk like this, so I'm going to limit our view a little bit. We're going to be focusing on two-dimensional smooth manifolds. Two-dimensional means that you walk around it like it's a surface, like the surface of the Earth. That's two-dimensional. And smooth means that it's nicely behaved. And you get into the weeds when you start talking about it. So it's infinitely differentiable, if you know what differentiable means, which you probably do. But yes. These are known as Riemann surfaces. These are three examples. This one looks all twisted. This one over here looks all twisted. That's just a torus. It's just this one over here. It's a double torus. Genus 2, for those who know. And this one is a hole through a hole and a hole, which I thought was so great. I just had to. Right. Now, atlases are good at describing structures on manifold, but not necessarily good at describing generalized maps. Did you have a question?
Well, no, just
Okay.
learning something new.
Is necessary, but yeah, so an atlas is good for describing structures on manifold, but it's not necessarily good at describing generalized maps. So, let me think about a map. So if I have the Earth here, and I want to talk about this patch, then I draw some sort of map, say this is South Carolina. There we go, Stereo. And that, if I want to talk about a path that I go off, so like if I want to talk about a path where I go around the world, the atlas isn't going to be able to describe that because the atlas necessarily maps into Euclidean space, two-dimensional in this case. And the map requires, so Euclidean space is infinite dimensional, goes off the blackboard. And so when you map from something that isn't infinite, it's compact, into a flat infinite space, you have to have boundaries in the image. And so if you leave the boundary, generalized path, you leave this edge, the atlas no longer works. So how do you talk about this in general? We're going to get to that a little bit later. It's helpful if you can collapse a larger space down onto the map. If I could talk about a path in infinite two-dimensional space, and then translate that back into a path on the sphere, then that would be helpful if I could go backwards. But in order to do this, you have to be careful. You have to be intelligent about how you put things together. Pretty good. Right. Now, for 10,000 years, mathematicians suspected that the fifth postulate, parallel postulate, wasn't necessary as an assumption. Excuse me. That you could prove it from the others, as I've stated. But it turns out that you do need it. In the late 19th, the early 19th century, mathematicians, including Lobachevsky and Gauss, presented a systems of postulates that included a variation on the parallel postulate, giving rise to an entirely new geometry. This is this thing. Okay. Now you can see that. We'll have pretty good face, to be honest. So this is where we start to leave Euclid behind entirely. Before, we were just taking Euclidean rules and generalizing them to these two-dimensional spaces, maps, or we map. Now we're leaving it entirely behind by going into a space where one of Euclid's postulates is not true. Okay. There. So now we have a new parallel postulate. This one says that given, let me to erase myself so I can draw at the same time. So all the same rules apply. So you can have, if you have 2 points, you can connect them with the line segment. If you have a line segment, you can extend it into a line. If you have a point and a radius, you can draw a circle. And all right angles are the same. So you can fit the same number of points, or same number of angles around the single point. But now, if you have a line and a point, then it's not, you don't have a unique line going through that one. Now you have at least 2. Yes.
At some point, those two lines will intersect the parallel line.
Yes, in Euclidean space. This board, this blackboard, Euclidean space is the space of the blackboard, it's flat. And so I can't really draw hyperbolic space. That's the issue. Now, the thing is, I'm using the blackboard as an atlas. So here, and hyperbolic spaces are manifolds, I should mention that. So there is an atlas from hyperbolic space into Euclidean space. I've just selected a patch, and I've selected my function so that the straight lines appear to be roughly straight. Just imagine that you don't really see what's going on past this. These 2 lines, they are straight in hyperbolic space. And they never touch this line. It's a little bit of a jump because you're very right. We've been studying Euclidean geometry for so long, comfortable with Euclidean geometry. So this is a new concept. It may be difficult to think about the first time. But this isn't an accurate representation of it. In order to give an accurate representation of Euclid of hyperbolic space, I have to have a warped board, a hyperbolic shaped board. And I don't. So I have to draw it in inaccurate place. So we're just going to say that these two lines never intersect this one. But there are at least two lines through this point that go through it and never touch this line. Okay. Now, if Euclidean geometry is the geometry of straight lines on a flat space, then hyperbolic geometry is the geometry of straight lines on a hyperbolic sheet. This is the easiest way to think about it. If this campus is flat, then we have Euclidean geometry. If this campus is a hyperbolic sheet going up away from a particular point, then the paths on it are hyperbolic lines. That's going to follow hyperbolic rules. It's also the geometry of other things, such as the geometry of lines and circles that intersect the unit circle at right angles. I want to draw a picture of this one too. This is called the Poincaré disk model, and I love it. So, we're familiar with Euclidean geometry. It's just the set of lines and points and circles, angles, etc. If we were to instead define a line to be something else and talk about behavior in that space, we might end up with a different looking reality. So we start with the unit circle. This is now our entire universe. Everything exists inside this place. And it's a bit of a preview. It's right here. Now, we're going to define lines to be straight lines, or Euclidean straight lines, that go through the origin. And circular arcs that intersect the edge at right angles. What does it mean for a circle to intersect at right angles? Well, you look at the tangent lines at those points. If they intersect at right angles, then these circles intersect at right angles. Now, in this space, if you have any 2 points, you can define this one's tricky. A circular arc that connects them. Or if you can't, you can at least define a straight line. This is not trivial. It requires proof. I don't have time to do a proof. So, take my word. Second, if you have any kind of, well, that's not right. If you have any kind of circular arc, you can extend it indefinitely. This one is also trivial, because I have to show that I can define a metric on this where distances grow arbitrarily large as I get closer and closer to the edge. Also not trivial, also requires proof. Take my word. Then the third one, you can define a circle. That one's relatively easy because I said that there's some sort of notion of distance. I can have all the points that are a particular distance away from a point. So I have circles. And angles are the same because they're inherited from the Bible. They're inherited from Euclidean geometry. So all right angles are the same. Now, last one, for a particular line and a point not on that line, I can draw at least 2 lines, quote unquote lines, that are not on that line, that go through that line. So this space, if these are our lines, straight lines through the origin, and circular arcs that intersect the unit circle at right angles, this follows hyperbolic geometry. So, and that's what this is. What I've done here is I've taken the hyperbolic sheet and I've projected it down onto this unit circle. This is an atlas.
So like 3D, like 3D graphing of some sorts.
Do you need 3D graphing?
Well,
Yeah. You can't So part of the thing about hyperbolic geometry is that it's not clear. So you're not going to be able to represent it with Euclidean rules on a blackboard or on a computer screen. You always have to warp it in some way. It's like with a map. If you take a map of the Earth and you map it down onto Euclidean geometry, onto a map, on a piece of paper, you either have to flatten something like Greenland becomes huge or lines become a little bit dense, stuff like that. Same thing with this. If you want to get an accurate representation, you can embed it in 3 dimensions. So you can plot it in 3-dimensional space, but if you want to do it on 2-dimensional space, you have to warp things. And that's why we get these things where straight lines no longer appear to be straight. Because the mapping is trying to preserve angles. This particular mapping, trying to preserve angles. It's not trying to preserve the straightness of lines. There's another map that also maps into the unit circle, and it preserves straightness, but it doesn't preserve angles. So this stuff gets complicated. Was that clear? Okay. Now, in hyperbolic geometry, shapes work different. I'm going to try to go through a bit of a geometric. I keep on placing the eraser on one side. So, in usual Euclidean space, if you have a line, let's say that I have some sort of starting point, and I want to leave this line at a right angle, go straight up. Then we have our parallel line here, and now we want to talk about the collection of paths that would eventually take us back to this line. Well, we're familiar with Euclidean space. What are some paths that would take us back to the original line? Anyone's going down, right? Yeah, so anything that's below this line, no matter how close you get to it, eventually it's going to take you back to this point. So half of the plane will take you back. So, and this is one of the main defining features of how shapes work in Euclidean space. But in hyperbolic space, same situation, starting point. You go up at a right angle. Now, this is our ending point. Again, we're doing an atlas. We have 2 lines that never go back to this line. And also, as a little side thing, as soon as you have 2, you have infinitely many. Because since you have a continuous space between these, any line that goes through this, between these 2, will also never go back to the original. Because, yeah. But everything here, so we have these 2 limiting lines. They exist, I'm not going to prove that they exist. But this is the limiting line. Anything below this will take you back to this path. Any path below this one will take you back. So we have an arc. It's not the entire thing. Over here, it's pi radians. Over here, it's less than pi radians. Almost got the first. All right. Now, here's the thing. Since this space is translation invariant, that's something. Since it does not matter where you are in this space that controls the behavior, at every single point, the behavior is the same. This works the same way at every point along. There's another step I needed to make. So, since right angles are preserved, all right angles are the same. There is a unique line that intersects this path at right angles. Now, everywhere along that particular line, the paths that will take you back to this are the same sort of angle. Collection of different paths that will take you back to the order. So we have this sort of situation. We have cones that will take us back. Now we want to go from this right angle line and continue on. Same path, right angle. Now, same sort of situation. Same distance, same angle. cones that will take you back, now not to this line, but to this line. But there's an added wrinkle. If, suppose that I talk about this line, I follow this path to here, I might not necessarily be in this cone anymore. So if I continue on, I'll miss this cone, and I will never actually get back to the line, even though I was in this cone on this. But over here, this one will. So the situation is that the cone of lines that will take us back to our original line has gotten more narrow. This is one of the major defining features in hyperbolic geometry. The farther away you go from a line, the more narrow the cone of backwards paths becomes. So, if we want to talk about a triangle, the farther away one of the vertices gets from the opposite side of the triangle, the more narrow that one becomes. So, in Euclidean geometry, you can just keep on scaling up and up and up and up, and the angles will still stay the same. But in hyperbolic geometry, you get these really pinched angles way at far ends if you keep on getting bigger. And also, another side thing, triangles have a maximum size. I have no idea how to prove that, but I know it's true. The maximum size is actually pi. If it has curvature one, so blah, 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 blah. That's getting deep into the weeds. You can construct this triangle, but the sum of its interior angles always has to be less than pi. Further, the larger it becomes, the smaller those angles become. And this is kind of the opposite of the way it was with a sphere. If you're on a sphere, the interior angles had to always sum to greater than pi. Here, the interior angles have to always sum to less than pi. And yes, this characterizes all potential spaces. It's either equal to pi, less than pi, or greater. You can, like just in Euclidean geometry, you can construct any polygon from triangles. You can construct a square from 2 triangles. You can construct a pentagon from 3. You can construct a hexagon from 4. An octagon from 7. From 6. And by making these polygons larger, you can make their points, their corners, arbitrarily tight. And so because we have that the fourth postulate of Euclid still in place, where all right angles are the same, the behavior around a point is the same. But now angles of polygons have changed behavior. So now for any point, I can fit arbitrarily many squares around that point. These are all squares. It's weird to think about.
But is squares in hyperbolic space?
In hyperbolic space. Because I've made them so large that the angles are small enough that I can fit this many now. Does that make sense? I would not be surprised if it didn't make sense. Because this is an alien concept. The idea that a square doesn't have to have right angle corners. In fact, moreover, it has to have at least one corner that is less than a right angle. Okay. You can also have a pentagon with right angle corners. There's this. Really weird. You can fit arbitrarily many polygons around a point, and thus, since you can do that at any point, and these are regular polygons, you can take any polygon and tile the plane with it, any uniform polygon. Now, we've already examined the idea of considering a manifold in terms of an atlas, and this is a good way to express structure, preserve structure in some way. But now we want to wrap back around and talk about collapsing larger spaces again. do this, I want to introduce the idea of a quotient. So half the people in here are graduate students, half are undergraduates. So I assume that graduates know what a quotient is. Maybe you don't know, so but I'm going to go over what a quotient is like. I'm going to give it colloquially a description of what a quotient is. In short terms, taking the quotient of a space means that we take parts of that space and set them to be equal to each other. So, many ways to do this, and we can do it on a lot of different spaces. Yes. Right, sure, over here. Circle right there. I'm not gonna do a circle. I'm gonna find boundary. I suppose I am gonna do a circle, but it's going to be a very badly drawn circle.
Are we still in hyperbolic space?
Alright, okay, yeah, fair. Leaving hyperbolic space behind.
Okay, cool.
Hyperbolic space, we've set our, the big, like it's big concept, so. Hyperbolic space, big takeaway is that angles behave based on distance. And you can tile it with any kind of polynomial. Big takeaways. Now over here, we're starting with the square. I'm going to be talking about a quotient. Someone's read this one just now. Right. So the quotient, we're going to quotient this. What this means is we're going to take some collection of points and set them to be equal to each other and say that they're the same point. And the way that we're going to do this is we're going to take the top edge and we're going to identify it with the bottom edge. What is the way that we identify these things together? For an arbitrary point down here, just any old point, we're going to say that it's the same point as the point directly above it on this line. And we're going to do this for all points along both edges. And I want to make sure I'm clear. This isn't Euclidean space. This isn't a hyperbolic space. This is a square. So, a square, and we are identifying the top edge and the bottom edge. What's the result of just that? Just that, a two, right. So what happens is you wrap it around. This is the same thing as just taking this point or this edge and this edge and gluing them together, saying that they're now the same. I took a welding stick and went straight across. And this is that top edge. Now, we're going to take another step. We're going to take this edge and identify it with this edge. 2 points are now the same if you can take it straight across to this point with a straight line. Now, these two edges are going to be wrapped together. Again, what we end up with is a double or a complement, depending on what day of the week. Oh, complement. Like in topology doesn't care about angles or lines or anything like that. It just cares about how the spaces connect. And the homology groups just talking about whether or not you can take a path on and collapse it down enough, all that stuff. But
Did you smoosh a cylinder? I don't know.
not better.
Well,
So from this step to this step, right? So I'm gonna draw a little intermediate step over here. Oh. There you got it. That. So. And these little tildes and the arrows, they're just saying that I'm making these be the same. So this goes up.
maybe I don't know.
And there's a little graphic. That's how that works. So. The torus I've already said is a manifold. I can map the surface of the torus with an atlas. You might have to be careful about it. I'm going to go ahead and grab this. I have to be careful about it, but I can do it. And I'm actually doing pretty good on time. So I might pause. Do you guys have any questions? Anything that's not making sense? Anything I could go on like this?
Could you share another example of maybe a quotient?
Sure.
Whether it be numbers or groups or just something more
Circles.
elementary?
A clock. All right, so we can talk about integers here. Everybody here knows what an integer is? So like you can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 blah. You can talk about a subset of the integers and say that, like, we want to look at all the ones that are different by 12. We say that if two numbers differ by 12, we're going to quotient them out. We're going to say that they are the same element. We'll end up with a clock where you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But then when you add 1, that's 13. 13 is 12 more than 1, so it's back to 1. 1, 2, 3, 4, 5, 6, 7, 8. That's called modular arithmetic. And if you get deeper into math, as you get deeper into math, you see that more and more often because it's very useful to talk about. There's a lot of things in math are quotients, but was that satisfactory? And we're also going to be talking about other ways of constructing the torus here in just a second. Now, right now, actually, if I want to take a quotient of Euclidean space, construct the same torus. So this is that thing that I was previewing before, where I want to take a larger space, an infinite space, and collapse it down to a more familiar space. We can do that, but we have to be careful because the torus is finite, it's compact. If you know what compact means. It's compact, but Euclidean space is infinite, it's not compact. So you're mapping an infinite space down onto a finite space. The way that we do this is we start out this is Euclidean space I'm going, a tiling of squares. Or on the floor, we have tiling of squares. Squares. Okay.
Is each square the same number?
Yeah, exactly. So what we're doing is we talk about the total collection of motions we can have in Euclidean space. I can start here and go here. Or I can start here and go here. I can go here. Go here. But then I want to talk about, so that's a set of all motions in Euclidean space, which also happens to be Euclidean space. Now we consider the space of all, so we consider the space of all motions. And then we take all motions that take the unit square, this one. We take all motions that move this square onto another square so that it matches up. The tessellation appears as though it hasn't moved. So this goes up to here. This motion that will take this corner to this corner, this corner to this corner. Those motions are all the same as not moving. Then we get the torus. Why? Is it obvious or is it not obvious? All right. So does that need further explanation? Yes, I think that's fine. All right. General idea here is that if we start with this torus, I move up by 1, starting here. And I go up by 1. This takes this square and puts it on top of this square. But what happens to a point inside this torus? It goes from here straight up to here. And so what we've said is that this, the same thing is not moving. Thus, this point must be the same as this point. So by saying that this kind of motion is the same as not moving, we've said that this square is the same as this square. Same thing here. If you move it directly right one, you can move this point to this point, which is the same as not moving. So this edge is the same as this edge. So what we've done is we've taken the entire Euclidean space and we've mapped it down onto a torus. And this is where generalized paths can be described in this way, like with Euclidean space. Because we're comfortable with Euclidean space, we can talk about paths in Euclidean space. We just look at where we end up. And then we just take this quotient and see what corresponding spot in the original square we would end up in, and that's where we end up on the torus. So, big concept, taking this big space down to the small space. But the big thing is that we've split up Euclidean space into all these different copies of the square. And so that is what allows us to collapse everything down into the torus, because we know how to do it from a square. Now here, what we want to do is we want to figure out a way to capture that on Euclidean space. Let's see. Yeah, I'll do the next part in this next. But because we can do this tessellation, we can map Euclidean space onto the torus. If you are more familiar with quotients, this is the same thing as taking R2 and quotienting out by the integer lats. If you aren't familiar with this terminology, don't necessarily worry. You'll see it eventually. But yeah, this is the same thing as the torus.
I just noticed that those are the same letters that you use for the set of real numbers and the set of integers.
Yeah, that's because they are. They're the exact same thing. Don't worry necessarily if you haven't seen it yet, because you'll eventually see this. Keep on pressing watching. They are the same. Euclidean space, like real numbers, that's one-dimensional Euclidean space. And if you want to talk about a tiling of the plane by squares, the corner points are the integer lattice points inside two-dimensional Euclidean space. All right. Now, we're focusing on Riemann surfaces, which are like what I mentioned before, like manifolds are this huge space. You can talk about any sort of map from any kind of space into Euclidean space. So there's a whole bunch of manifolds. We want to restrict our views so that we stay same. So we're just focusing on Riemann surfaces. These are manifolds that have complex dimension 1. That means that they're flat. You can walk around them as if they were a surface, like the Earth. Your Earth is a Riemann map, or is a Riemann surface. Now, if they're compact, the Riemann surface is compact, that means that you can hold it in your hands. Think about it that way. If it's compact, then it's characterized by the number of holes it has. And this number is called the genus of the surface. A sphere has genus 0 because it doesn't have any holes. Also, Euclidean space is a manifold because you can map Euclidean space into Euclidean space. It also has genus 0, but it's not compact. So it's a torus has genus 1 because it has that single hole in the middle. Other compact Riemann surfaces have greater genus. So if it's compact and it's a Riemann surface, it's characterized by the number of holes. And this is the thing that we were talking about before. A 2-hole torus has genus 2, a hole and a hole and a hole. That has genus 3. And showing that that has three, genus three is a little bit ahead of that genus three. Now, in general, compact Riemann surface of genus greater than 0 can be realized as a quotient of a 4 in big sets. So before, we already showed that you can take a square and turn it into a torus. Torus has genus 1. Square is a 4 times 1 god. It's a 4 god. How do you get a 2-hole torus from an 8 god, from octagon? I'll show you that now. I'm just going to show you 2 different ways of doing it. In general, so we have this. So that's MS. And then we have another one, double, straight line, straight line. So we have 2 different tori here. And we want to get to this guy. I'm going to show you how to construct this from this. So first things first, we want to bring these guys together. First step, we're just going to make them touch. So that's our first step. What does this look like in our squares? We're going to bring them together. We're going to make them touch at some point. I've decided to make that point be the corners. Now, let's pause for a second. We want to go from here to here. In order to do that, we have these guys touching at one point, but here they're touching at a circle. So what we want to do is we want to go from a point to a circle. What's that? That's like, so let's just say that we can do that. But what does that look like over here? Diagonal. Diagonal line. Yeah, you're right. So the thing is that when we were talking about this, a vertical line, that's the same thing as a circle over here. So circles on the torus are the same thing as straight lines on the plane. So if we want to take this point and turn it into a line, it will become a bit like this. Oop, 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 oop. Now I'm going to mark which ones are which. Then this was the original line. This is this guy. This is this guy. So from an octagon, we get a 2-hole torus. And you can do this in generality. You can build up however many holes in the tori that you want, just by keeping on plugging on more and more squares. But there's another way to do it, and I will also show you. So I'm going to start with the octagon. Then what I'm going to do is I'm going to identify this edge with this edge, this edge with this edge, this edge with this edge, and this edge with this edge. So we wrap this side and this side. And that gives us a shape that looks a bit like this. There's a little bit of work done down here that I'm kind of glossing over. But we go from here to here. Then this is the X, this is the X, this is the O, this. And now, when we wrap this around, we get 1-hole torus with 2 extra pieces. And then we wrap that around, we get another part of this. So this is another way. Try and handle this. Pretty good. Well, that's another way of getting the two-hole torus. Can everybody see that? Okay. And this way is actually a more relevant way to what I'm about to talk about. But if you want to realize a compact Riemann surface of genus greater than 0 as a quotient of an infinite space, that space has to be tiled by 4 n-gons. Exactly proving that takes a little bit of work, but it uses the intuition that I was showing you with the square tilings, where you talk about the ways that you can move across the entire space and quotient out by the ones that leave the tessellation as though it had not moved. So if you can tile it by regular 4 n-gons, you can quotient it out and you get the manifold that you're trying to get. So this ties it all together, a connection between hyperbolic space and Riemann surfaces. Since you can tile hyperbolic space with any kind of polygon at all, you can always realize a compact Riemann surface of genus greater than 0 as a quotient of hyperbolic space. So if you understand hyperbolic space, you can apply this understanding to just about any Riemann surface, because they're all contained in it. That's all I really have.
Questions?
Yeah, question.
I have some questions on the first part when you were explaining about the atlas. So this, when we are dividing X in subsets, these subsets, what happened with the intersections and, or they don't have intersection at all?
They do, they can have intersections. I was kind of glossing over that because I don't want to get into the weeds. But there's sort of a situation like what you want to do is if you have, make sure that I remember this correctly. If you want to talk about a smooth map, this is where we were talking about with Riemann surfaces. Riemann surfaces are smooth. So let's say that I have some sort of a shape up here. This is a region in my map. And then I have this other region. So this is U1. This is U2. And then B takes it to a nicely behaved space in Euclidean space. And then B1 takes it to a nicely behaved space, Euclidean space. On the overlap, can you see that?
Yeah.
Inverse composition.
Yes.
To be infinitely differentiable.
Yes, yes. The map here, from here back to here. That has to be infinitely differentiable.
The map in the overlaps or just in?
And the overlaps. And the specific and the overlaps. If it's infinitely differentiable, then you have a smooth map. If you can define an atlas where the properties. So the idea is that you go from here up to here, and then back down to here.
Other questions?
Yes.
What genus would like a t-shirt have?
Well, I think four, yeah, four. I had to prove it to myself for a second.
16 after I won it for a while.
What's your favorite manifold?
Yes.
The hyperbolic space.
Doesn't have to be.
But that is definitely my favorite manifold.
Okay.
Oh, I guess you did make the argument. Time bottle time. So like, I don't really know all the manifolds. Might be some really interesting ones.
They can go through strip up that.
Oh, how about infinite dimensional Euclidean space? That's a map.
That's disgusting.
Other questions? Let's thank our speaker. I think we do have an announcement here. Let's see. You might need to help me here.
Okay.
Get Alice back.
I would like to share my screen.
We probably stop recording. Yeah, we can stop recording. I guess.
I'll watch the question. I'll let you go.
Oh, wow. Okay. Oh, there she is. Oh, Dr. Lee is going to tell us about math 6550 for the spring, correct?
Yes, yes. Hello,
Okay.
hello. I'm Alice Wu. If you are interested in today's talk, please consider taking the course Math 4550 Topics in Geometry. The topic cover depend on the instructor. I will teach the course next semester. It will cover projective geometry, inversive geometry, and hyperbolic geometry. So all these are non-Euclidean geometry. They do not satisfy the axiom that mentioned at the beginning of this talk. We will not able to teach as deep as today's talk, but we will learn some basic and then learn them well. This course requires linear algebra, but very little calculus. It is suitable for junior and senior students. Since it is not offered every semester, not every year, if you wish to take it, please don't put off, otherwise you may be disappointed. If you have any questions about the course, please feel free to contact me. Thank you.
Thank you for getting back here. So consider that, tell your friends, and don't forget to rule out club. All the pizzas got to be gone, so take it on. Thank you all. We'll see you next week.
Dimensional
See you later.
space. Which cardinality and which